we had seen that Pn of x, that is the solution of the Legendre equation. And we have Pn of x and Qn of x. These are two independent solutions of the Legendre equation. And we wrote the most general solution. The most general solution of the Legendre equation as y equal to a Pn of x plus b Qn of x. Okay, so this is the most general solution of the equation. Then we are going to have the Rodrigues formula. The Rodrigues formula for the Legendre function Pn of x. Okay, and using this formula you can obtain the value of the Legendre polynomial. Okay, Pn of x is given by 1 over 2n n factorial, the nth derivative d raised to n dx raised to n x square minus 1 to the power n. So we are going to prove this. For proving this, we start from this step. Let v equal to x square minus 1 to the power n. Okay, v is x square minus 1 to the power n. Now as we differentiate dv by dx, we will get n x square minus 1 to the power n minus 1 2x. Okay, so this is our dv by dx. Now we multiply both sides by x square minus 1. Okay, then we get this x square minus 1 dv by dx. We are multiplying both sides of this equation by x square minus 1. So we have x square minus 1 dv by dx equal to n into x square minus 1 to the power n. As we multiply x square minus 1 to the power n minus 1 with the x square minus 1, you will be getting x square minus 1 to the power n, 2x, 2n. So this is equal to 2n vx, because we know x square minus 1 to the power n. This is v. Okay, this is v. So we get this as 2n vx. Okay, so we have this equation 2, which says x square minus 1 dv by dx equal to 2n vx. Okay, this is equation 2. Now what we do, we differentiate the above equation n1 plus 1 times. Okay, we differentiate the equation to n plus 1 times by Lebanese theorem or Lebanese formula. Okay, so what is Lebanese formula? This is the Lebanese formula. Suppose I want to differentiate product of two functions u and v. Okay, u and v, two functions. Then the nth power of this product, that is given by nc0 d raised to n u dx raised to n v, nc1 d raised to n minus 1 u dx raised to n minus 1 dv by dx. Okay, then nc2 d raised to n minus 2 u dx raised to n2, d square v dx square, then this n square minus 1 nc nu d square n v by dx raised to n. Okay, so this is the Lebanese formula. Lebanese formula is used for obtaining the nth derivative of a function, the nth derivative. So nth derivative of product, so it is this. Okay, we start from nc0 here, and then nc1, then nc1, then the last term is ncn, u d raised to n dx raised to d raised to n v dx raised to n. So this formula we are going to use. Okay. So when we apply this formula here on the left hand side, here we have x square minus 1, then d raised to n plus 2 dx raised to n to v. Why? Because we are differentiating this n plus 1 times. Okay. Then n plus 1 c1. You differentiate this 2x. X square minus 1 is 2x. That is written here. D raised to n plus 1 v dx raised to n plus 1. Then n plus 1 c2. As we differentiate this 2x, we get 2. Okay. So this 2x is obtained by differentiating x square minus 1, and then we differentiate 2x and you get 2. And the next time you have to differentiate 2, so you will be getting 0. So this is what you get on the left hand side when you apply the Lebanese formula. Then if you take the right hand side, here we have two functions v and x. Okay, v and x. So you get x d raised to n plus 1 v by dx raised to n plus 1 here. Then n plus 1 c1. You differentiate x, you get 1. Then d raised to n v dx raised to 1. Okay. So this is what you get on the right hand side. And here we know NCR that is equal to n factorial over n minus r factorial r factorial. So using this we have to find NC 0. So what will be NC 0? N factorial over n minus r is n factorial 0 factorial, and that is equal to 1. Okay. And same way you have to find the other teams as well. Okay. So you will have here on the left hand side this, and on the right hand side this, and as we combine these two, okay, as we combine these two, you will be getting this x square minus 1, here d raised to n plus 2v dx raised to n plus 2 plus 2x. We have this n plus 1th derivative here on the right hand side, and here we have the n plus 1th derivative on the left hand side. As they combine, you have this 2x n plus 1 c1 minus n. Okay, then you have this 2n plus 1 c2 minus n into n plus 1 c1 d raised to n dx raised to n equal to 0. So as we combine or take the terms on the right hand, the right hand side to the left hand side, you will be getting this. Now what is n plus 1 c1? N plus 1 c1 is this, n plus 1 c1 is this, n plus 1, and n plus 1 c2 is this. Okay, n plus 1 c2 is this. This is n plus 1 c1. So as they combine, you get this x square minus 1 d raised to n plus 2 dx raised to n plus 2 v, 2x d raised to n plus 1 v dx raised to n plus 1. This one you get like this, and as they combine, these two combine, you will be getting minus n into n plus 1. Anyway, the final expression will be this x square minus 1 d raised to n plus 2 equal to d raised to n plus 2 dx raised to n plus 2. Yes, so you will be getting this differential equation. See, here you have the n plus 2th derivative, here you have n plus 1th derivative, here nth derivative. Okay, and this is basically the Legendre equation. Suppose you put y as equal to this d raised to n v dx raised to n. Suppose y is equal to d raised to n v dx raised to n. Then you will be getting this. Okay, and this is exactly the Legendre equation, Legendre differential equation. So we put d raised to n v dx raised to n equal to y in the previous equation. So you will be getting this. Okay, and this is the Legendre equation. And you know the y which is equal to d raised to n v dx raised to n, that is a solution of the differential equation, and the solution of the Legendre equation is Pn of x. Okay, so this y that is equal to Pn of x, that is equal to y is equal to Pn of x. Okay, because this is Legendre equation. So one can write, since y is d raised to n v dx raised to n, one can write c d raised to n v dx raised to n, that is equal to Pn of x, where c is some constant which we have to determine. Okay, why we are writing like this? Because we know this is the Legendre differential equation and its solution is Pn of x. So this y, which is d raised to n v dx raised to n, that can be written equal to Pn of x, or we write this as c times d raised to n v dx raised to n, where c is a constant that we later determine. So for determining the c, what we do is we start with this. We know v is x square minus 1 to the power n. We know v is x square minus 1 to the power n, which can be written as x plus 1 to the power n into x minus 1 to the power n. Okay, so this can be written as x1 plus 1 to the power n into x minus 1 to the power n. So two functions u, v. Okay, so I am finding this d raised to n v dx raised to n, the nth derivative of this. Okay, so two functions are here, so we use the Lebanese formula again, and it can be written like this: nc0, we are taking nth derivative, x plus 1 to the power n, d raised to n dx raised to n, x minus 1 to the power n. Okay, this is kept like this, and this nth derivative is taken, then nc1, as you take the derivative n, x plus 1 to the power n minus 1, and here we have d to the power n minus x raised to n minus 1, x minus 1 to the power n, the n minus 1th derivative of x minus 1 to the power n. Okay, and the last term will be this. Okay, last term will be this. See, so all these terms contain x plus 1 to the power n and x minus 1 to the power n and their or their derivatives. Now x minus 1 is a factor in every term except the first. Okay, here x minus 1 to the power n, that will not be present here, or x minus 1 will not be present here. As we take this derivative, nth derivative x minus 1 to the power n, you will be getting n factorial. Okay, you will be getting n factorial. So this derivative, this will be equal to n factorial, that you can check. Okay, So that is n factorial. Then this is n factorial, but when you take the n minus 1th derivative of x minus 1 to the power n, okay, d n minus 1 dx to the power n minus 1. So n minus 1th derivative of x square minus 1 to the power n you are taking. So you will have a n minus 1 term here. Sorry, what is it? You will have an x minus 1 term here, and all these terms contain the x minus 1. Okay, so one can say, as we put x equal to 1 in this equation, that is, we find the derivative when x equal to 1. Okay, so since all these terms contain x minus 1, the factor x minus 1, when you put x equal to 1, this will be 0. Okay, so you will have only the first term. Okay, so you have the first term. First term here, when you put x equal to 1, it will be 2 raised to n, and here you will get n factorial, so that is written here. So d raised to n, sorry, this is d raised to n, nth derivative of v to the x to the power, that is 2 raised to n factorial. Okay, so when we put x equal to 1 on the left hand side, sorry, on the right hand side we have we have this c 2 to the power n factorial equal to, on the right hand side, Pn of x. See here it is Pn of x. So when you put x equal to 1, this will be Pn of 1. Okay, so we have this c 2 to the power n factorial equal to Pn of 1, and Pn of 1 is 1, that you will prove later. Pn of 1 is 1. So one can say c is equal to 1 by 2 raised to n by n factorial. Okay, now substituting this value, we have determined the value of this constant 1 by 2 raised to n factorial. Okay, substituting it, you will get Pn of x as equal to 1 by 2 raised to n factorial. C is this, d raised to n dx raised to n, or p raised to n x is 1 by 2 raised to n factorial, the nth derivative of x square minus 1 to the power n. So this is Pn of x. We have proved it. Okay, now using this we can determine the value of P0 of x. P0 of x means the derivative. You need not take the derivative. So you will have when n is 0 here. So you will have here n is 0, so you will be getting 1. So P0 of x is 1. P1 of x, we have to differentiate this one time. So d by dx, so you will be getting x. P2 of x, this will be 1 by 2 square, 2 raised to factorial. You have to differentiate this thing 2 times if you are finding P2 of x. Okay, and you will be getting this. Finally, you will be getting this when you take the second derivative, d square by dx square of this. Okay, same way you can determine P3 of x. You will get this P4 of x, P5 of x. Also, you can plot this P0, it is 1, the value of P0 is 1, so that's why you are getting a straight line here. P1, it is x, so that's why you get x, that's why you get a straight line like this. Okay, because P1 is x, so as x increases, P1 also will increase linearly. And this is P2 of x, this is P3 of x. Okay, so you can get the various P0, P1, P2, P3, etc. Okay.